I'm Henry, and I'm a specialist at the Division of Mineral Resources and Applied Geology at the Taltech Department of Geology. And I'm encouraging you to think about the impact and the actual talent that different minerals and resources have in our everyday lives. This is the growing population of the world. It is 8+ billion people living on the planet at this very moment. We reached 8 billion last year in 2023, and we are expected to reach 9 billion in the year 2037. That is in 13 years. So there's not that many or much time left until we reach another billion of people living here on the earth. Yes. Intensive urbanization and globalization, economic growth, as well as higher expectations for better living conditions, clean energy transition to reduce climate warming, including the renewable energy, storage batteries, and electrical vehicles, as well as the overall technological development, all actually lead us to a growing demand for mineral resources, water, and energy supplies as well. So what do we need the mineral resources for? Yes. We all use some kind of transportation, either it is a car, public transportation, either it is an electrical scooter or a bicycle. We all want to have some sort of an electronics. We want to have a computer that we're listening to this webinar. We want to have a mobile phone. And of course, we want to have a roof or a house that we can live in. And there's actually more and more and more and more of things in our everyday lives that actually come from mineral resources. So as well as even the building you're at the moment is built from construction materials that come from mining, and the heating and the electricity that you're using, and also the food that we eat comes from some sort of, we can say, connected through fertilizers, but they also can come from mining as well. So on this figure, you can also see that a lot of different aspects of our everyday lives are connected to mining and to different resources, and they play as important role in people's lives as food, water, and air. So natural resources are resources drawn from the nature. They are soil and forests, they are sun, water, wind, rocks and minerals, and oil and gas. And to define what is a mineral resource, it is a rock, mineral, liquid, gas, or an organic substance found in the Earth's crust and whose extraction is practical and economically beneficial, so something useful for people can be produced. And for example, if you take an example from Estonia's or Republic of Estonian Constitution, we also have paragraph number 5, which states that the natural wealth and resources of Estonia are national riches which must be used sustainably. So it's even emphasized in our constitution as well. But there is a problem that the resources are in limited quantities. And since 1970s, we have used almost 1/3 of Earth's natural resources. And we need to use resources with lower qualities. However, as you can see on the graph on the right-hand side, that the global material extraction is on the rise. To that, we also need the equivalent of 1.86 Earths to provide us with natural resources for our current consumption. For example, if we lived like Americas, this number would be even higher. This would be 5 planet Earths that would be needed. But in globally overall, the number of planets that we need at the moment is 1.86. And because of that, because resources are in limited quantities, we also need to turn more to circular economy and use the materials that we've already taken to the circularity. So the question, how do we obtain the mineral resources? A little bit of ABC. The answer is by mining. So in overall, we have 2 types of mines. We can say we have surface mining technologies or open pit mines. You can see on the figure as well. And the other part is the underground mining technologies, which are used underground. And for example, the deepest open pit mine is only around 1 kilometer. in depth, and the deepest underground mine that we have nowadays on Earth is around 4 kilometers in depth. It's a gold mine, and it is in South Africa. Here you can see a picture of me and my colleague. We also went to Boliden mine. It's in northern Sweden, and it's a copper, gold, and silver mine. And actually, the point of this picture is actually to show you the vastness or the amount of actually the size these mines can have. And here in comparison, you also have one of the machines used in the mine, which is actually the diameter of the wheel is around 4 meters. So actually all these areas that are used for mining need to be rehabilitated afterwards as well. And there are actually different types of opportunities for that, and it really depends of the region and of the mines and technology used as well. In the world, we have different types of mines. Here in the picture, you can see it's an artisanal mine in the Democratic Republic of Congo in Africa. And here we can see that the workers have poor working conditions, and there is a really high possibility that they use child labor, as well as the cobalt in your mobile phones most likely is from the same region, from Congo, from South Africa, where workers have to work in these conditions where they don't have that much of machines, and they will have to use their hands to dig out the minerals. And in overall, these are the keywords that shape the contemporary landscape of the mining industry. It's the environmental impact and how to assess the impact and how to mitigate it, the social responsibility, the governance policies, and the economic uncertainty overall as well. What about the future mines? They're in overall human poor and robot rich. There might be electric vehicles, remote control, automation, drones, waste and byproducts management. A lot of those are already in use nowadays as well, but it will become more and more automated and robotized in maybe a couple of years, even more. And one day we could even be mining in the deep sea regions or even in space on asteroids as well. Shortly, what do we mine the most? The highest numbers of mining products actually comes from iron ore, which goes into steel making. The second largest part is industrial metals, where we can see aluminium, chromium, manganese, copper. And the least part of mineral resources mined are the technology and precious metals. And there we can find rare earth oxides. We can find there, for example, gold or the platinum group metals as well. Where do we mine? Is the question that we might have. Actually, we mine all over the world, but usually people say that not in my backyard. So what if I told you that will be a brand new mine opened 1 kilometer away from your house? Usually people wouldn't like it and they would say not in my backyard. But when we look at the pictures from people's backyards, all the, we can say the lawnmowers and everything, all they also need some materials that come from mining. So it cannot be like this all the time. And now next question brings us to how many old phones do you have at your home? You can think about it a little bit. I think I have at around 3 old phones at my home. I'm not using them, they're just staying there. But this actually is a really large fortune because nowadays 1 ton of mobile phones can actually have more minerals in concentration than 1 ton of metal ore. So the fortune in your living rooms can be even higher than the rocks that we can mine nowadays because their quality isn't that good anymore. And in the smartphones, we almost have 2/3 of the periodic table, and you carry it on a daily basis in your pockets or your bags. We can see, for example, that elements are used in mobile phones, electronics, casing, battery, and screens. And for example, if you feel your mobile phone vibrating, that is called rare earth elements, neodymium and dysprosium to it. But Tony is later on going to speak about rare earth elements more in depth as well. So what happens to our old phones? One thing is we gather them in our living rooms, and second opportunity, there's even more, but they might end up as e-waste. And there is actually a term called urban mining. So this is a concept that originates from 1980s from Japan, who wanted to be more autonomous and less dependent of materials that come from China. And actually, the goal of urban mining is to recycle precious metals and rare earth elements found in the electronic waste that is stored in the landfills that you can see also in the picture. And the stages and costs and challenges of traditional mining and urban mining are different. For example, for e-waste, it can be extremely complex in terms of physical and chemical properties to separate different elements from a mobile phone. And we need to collect them, pre-process them, and sort of on and on and on. So regularly, mining methods are actually more in nature for us, and we have more information and knowledge how to do it, and it's easier for us as well. A short introduction to green transition. So as you can see from the graph, the amount of raw materials that are needed for our daily lives has also changed and increased throughout the time. So, for example, in the 1700s, we only needed a couple of minerals, but in the 21st century and in the 2000s, we already need a couple of more and more elements for our daily activities. And this comes also from a green transition, and we want to use carbon-free energy. So this comes to the availability of all these several critical metals. And this graph ends with 2000, or the year 2000. You can already think what amount of minerals and materials and elements do we need in 2024. And I can think that the graph is actually going to increase more and more and more. And just to put it into a perspective, of the minerals used in different energy technologies. For example, in electric cars, the amount of all those different elements listed in the right-hand side is actually many times larger than for a conventional car. And it goes the same with, for example, wind energy, solar energy, compared to the nuclear, coal, or natural gas technologies that are used on a daily basis. So for these elements, yeah, we're going to need an increased future demand. For example, for copper, we can see the changes are drastical comparing the electrical car and conventional car. But one thing that we can be sure of that in 20, 30 years, we will still have wind and the sun will still be shining. So we can use those technologies. Shortly about critical raw materials. Which is actually a list created by the European Commission. There are 34 different elements which are of great economic importance and supply risk for Europe. And 4 of them actually can also be found in Estonia. These are the rare earth elements, the phosphate rock, and vanadium as well. And these, all the critical raw materials can be used for different purposes. And Tony is going to speak about that later on as well. Here you can also see that in Europe, we have potential for all these critical raw materials as well. For example, if we take a look on the map, in Estonia, we also have a cross for phosphate rock, and other potential regions in Europe as well. So we still need to develop these fields and do research and development, which are crucial for all these resources. The main term called circular economy, it is actually a closed loop system where the use of resource inputs and the creation of waste, pollution and carbon emissions are minimized. It starts with exploration, mining, processing, and so on to recycling. But you can see that there is waste created from each of these process parts, we can say. But it's actually the material that comes from the leftovers is still taken again to a new circle. And compared to the linear economy in the right-hand corner, we can see that there we have to take the materials, make them, and dispose them, and we do not have the circularity. Here is a good example of the aluminium can, which can become from a new can to an old can in 60 days. But all in all, because people don't recycle the aluminium cans, they don't bring them back, and all the different countries don't have the systems, we actually still need to extract new material. For example, bauxite, which is an aluminium mineral that is used. And if you compare the average lifespan to the optimum lifespan, we can see that extending the life cycle and lifespan of the products is actually an important part of the circular economy concept, so that we don't consume that many products, and those products that we have taken into the circularity, we can still use them and use them efficiently. And one good example from that is actually the Eiffel Tower in Paris. It was built in 1998 for the World's Fair. It was expected to be there for 20 years, but now 135 years later, it is still there and it has become sort of a monument. And we have many tons of material, iron, locked inside the Eiffel Tower. So this is a good example. If they would have taken it down, they would have gotten a lot of material into their circularity as well.